Good afternoon. Welcome to the Senior Design Expo 2021 by CalStat LA. We are a part of the Long Range Endurance Platform UAV team, Senior Design Team number 9. And in particular, we are the flight team. The team includes myself, team lead Miguel Ortega, and with me is Christopher Martinez, Alan Sosa, Mohamed Ghauri, Janice Arteaga, Jerry So, Marisa Munoz, and Luis Robles. Our team advisors are Michael Thorburn, Ronald Sobchik, and Ray Manning. Our project is in collaboration with the Aerospace Corporation, represented by Dr. Allyson, Yarbrough. At this point, I'll pass it over to Janice, who will introduce our project.
Hello everyone, my name is Janice. I'll be going over the agenda for our presentation today. So it will include the project objective, the flight team objective, the work breakdown, the UAV overview. The project results will be divided into 3 subgroups, which include the aerodynamics subgroup, the control component subgroup, the control system subgroup, and lastly, the summary. Our project objective was to design a hybrid powered UAV, which will have long-range capabilities up to 4-hour flight times, and it will monitor emissions from the ships at the Port of Long Beach. Our flight team objective was the flight team focuses on the aerodynamics and controls aspect of the UAV, designed by conducting aerodynamic analyses to verify that the proposed design is achievable. In addition, the sensor components were determined to best fit the necessary flight capabilities and design a control system model to achieve stable flight. Here we have our work breakdown structure. Again, our flight team was divided into 3 subgroups, which includes the aerodynamics, the controls components, and the control systems. In the aerodynamics, Miguel's work breakdown was the propeller design and performance, Luis's was the wind design and performance, and Chris was the aerodynamics analysis of the central fan. In the control components, Marisa's work breakdown was the power consumption for the sensor hardware, Jerry's was the sensors for determining position, and for our control systems, Alan's work breakdown was the Simulink modeling and simulation. Mohammed's was the Simulink modeling and analysis. And mine was the sensor fusion architecture. Our UAV overview. So the unmanned aerial vehicles are becoming more popular in a wide range of applications, aerial photography, mapping, and surveying. UAVs are cheaper and smaller than larger aircraft, rotorcrafts, and can serve the same functions as mentioned above. Sensor assembly, flight control system, fin and propeller design, and performance were investigated. Now I'll pass it back to my flight team lead, Miguel.
Okay, thank you. To start with, here's the original design proposed by the Aerospace Corporation. Their design consisted of a 7-propeller UAV, 1 ducted central fan, and 6 surrounding micropropellers. In addition, the original design included a hybrid powered vehicle with wings intended to maximize its flight time. The target flight time was 8 hours with a minimum of 4 hours. Finally, it was suggested that the UAV remain under 55 pounds to avoid requiring permits to fly. Throughout the school year, as the UAV design was being developed, the team got to a point where the 55-pound limit was surpassed. A vehicle with all the required capabilities fell above the intended limit. At this point, the team decided that obtaining required permits was best, and upon taking inventory of all the components incorporated in the design and those yet to be decided on, we declared that the maximum weight of the UAV will fall close to 100 pounds. The rendering on the right-hand side shows the team's current design. This model consists of a 2-foot in diameter duct with a 20-inch central fan. Surrounding the UAV are six 24.5-inch KDE direct propellers. All 7 propellers are connected to KDE direct electric motors as shown by the picture below. And finally, the 7 carbon fiber propellers have a combined weight of about 1.2 pounds. Here we look at an overview of our UAV model. The propellers are numbered 1 through 7 as shown on the right. And when considering forward flight, these 3 equilibrium equations are determined. Equation 1 considers the forces along the x-axis. This equation includes the horizontal components of the thrust when the UAV is pitched and the drag forces due to the wind. The second equation is the sum of forces along the z direction, which is composed of the vertical components of thrust and the weight of the UAV. The third equation considers the torques induced by the propellers about the z-axis. That is, if not balanced, this will result in the UAV rotating uncontrollably. For traditional UAVs such as quadcopters and even hex-copters, the even number of propellers allows for the torques to be balanced very simply. Half of the propellers rotate in one direction and the rest in the opposite. In our case, we have an odd number of propellers. The issue here is not simply balancing torques while hovering, but also being able to forward fly and accelerate vertically. In order to accommodate adjustments that the UAV will have to constantly make, we take a different approach at balancing the torques. In this case, the torque equilibrium equation was split into 2. The first equilibrium equation, labeled equation 3, considers the central ducted fan as well as propellers 1 and 4. This means that propellers 1 and 4 balances the torques induced by the central fan. Equation 4 looks a lot like that of a quadcopter's. The intention here is that these 4 propellers will balance each other's torques simply by 2 rotating in one direction and the other 2 in the opposite. In this configuration, these 4 propellers will rotate at the same angular velocity, and when adjustments are to be made, these 4 propellers will account for that. Here, we will briefly discuss some results found in the most recent forward flight analysis. Once again, the propellers and electric motors are made by KDE Direct, and the manufacturer provided performance data that was then used to more accurately determine the angular velocity that each propeller should function during forward flight at varying pitch angles. This analysis was done on MATLAB, and the table here shows the results. Here you can see the total thrust exerted by the UAV to fly at a given pitch angle without losing elevation. Also, you will see the resultant forward velocities and the energy consumed by the propellers per distance. This graph here plots the energy per mile at different angles of pitch. This graph allows for the optimal forward flight speed to be found. In this instance, the lowest point on the graph is at a pitch angle of 44 degrees, resulting in a minimal of 1100 kilojoules per mile. At this configuration, the UAV flies at a forward velocity of 30 miles per hour. At this point, I will pass it over to Luis, who will discuss some of his work done on the wings.
Thank you, Miguel. To determine the shape of the wings, the lift required had to be calculated using the lift equation. Lift is a function of the density of the air, the velocity at which the air travels, the lift coefficient, and the surface area over which the air flows. So all the values to calculate lift were known, except for the lift coefficient and the surface area. Since the lift coefficient is an unknown, an educated guess was made to choose a value for that variable. The guess was made based on the Reynolds number calculated at a specific max velocity of 60 miles per hour. The Reynolds number was calculated using the Reynolds number equation. That equation consists of the density of the air, the velocity of the fins, the characteristic length, and the dynamic viscosity of the air. A Reynolds number of 383,000 was calculated, and with that value, a lift coefficient of 1.0 was assigned. The next step was to calculate the surface area of the fin. To get a better understanding of the geometry of a fin, I used the wing geometry definitions from the NASA webpage to select the adequate dimensions. Dimensions such as the span of the fin, the base length, and the tip length. Next slide, please. This is the current wing design with a tip length of 5 inches, a base length of 10 inches, and a span of 12 inches. Based on those dimensions, the surface area of the fin is 600 inches square. The fins are hollow and made out of carbon fiber with a mass of 0.45 pounds each. We can also see the CAD model of the current wing design along with the airfoil that was chosen, which has the name S4310. Next slide, please. Here we have some alternative designs. For design A, the tip length was increased to 10 inches while everything else remained constant, a base length of 10 inches, and a span of 12 inches. Those dimensions resulted in a wing area of 1,200 inches square. For design B, the tip length was increased to 13 inches and the span was decreased to 6 inches, while the base length increased to 15 inches. Those dimensions resulted in a wing area of 1,100 inches square. Next slide, please. Now, since all the values are known, the lift at different velocities was calculated using the lift equation and tabulated in the following table. These values of lift are per wing. At 11.91 miles per hour, the lift obtained is 2.12 pounds or 4.14 pounds in total. The optimal speed is 29 miles per hour, and at that velocity, we obtain 12.79 pounds or 25.58 pounds in total. We generate the most lift at 54 miles per hour. We get 43.88 pounds, but that velocity is not ideal since we consume a lot of energy too fast. Lastly, we also have a flow simulation of the current wing design. Next slide, please. Now let's take a look at the fin efficiency. The question asked is, does the energy per distance change with the addition of the wings? Let's look at the table where we have the energy consumed per distance, which was calculated at different forward velocities. The third column has the values of energy per distance without the wings. The fourth column has the values of energy per distance with the wings. Let's take a look at one of the velocities. At 29.1 miles per hour, we get a value of 1,100 kilojoules per mile without wings. At the same velocity of 29.1 miles per hour with wings, we get a value of 810 kilojoules per mile. That results in an energy reduction of 26% when the fins are added. Overall, the wings do decrease the energy per distance when forward flying, and that difference increases as the velocity increases. Now I will pass it on to Chris, who will share his results. Thank you.
Thank you, Luis. Here, the analysis I will present is based solely on the effect of adding a propeller to the central duct. To determine if the addition of a central propeller was beneficial, the analysis focused on the increased thrust from the duct. Because the duct is not perfectly cylindrical and is not free of blockages, it was important to determine that the performance would not be impacted. Due to limitations this year, the analysis is purely theoretical. Next slide, please. Here, we break down the main points of the duct and how thrust is affected. The thrust is driven by the propeller, with the duct having a slightly decreasing radius, which in turn is believed to increase the thrust output from the propeller. This allows us to obtain a better performance from the central propeller. It also contains some blockages, mainly the engine and its supports, which would cause a drag effect that could lower the performance. Next slide, please. Here we have projected the theoretical values for a free propeller like the ones that are on the outside of the drone and the increased thrust when placed inside the duct. This analysis considers that the propeller inside the duct would be 20 inches in diameter and that no air is being compressed. Due to the duct shrinking, there is an increase in velocity of the air. For example, the velocity of the free propeller at 21 feet per second would approximately increase to 25 feet per second and therefore increasing thrust from 36 pound force to 86 pounds force, giving us a performance increase of about 140% when the duct is clear. Next slide, please. Since there is an engine inside the duct, a drag is produced. Here we have projected the effect that the blockages have inside the duct. Because the engine has a drag coefficient that cannot be determined without experimental analysis inside a wind tunnel, a range was chosen to see how big the effect would be. The range was determined by taking drag coefficients of known objects like a rough rectangular box to obtain the maximum drag and a thin plate for the minimum drag. Running the central fan at max speed can cause a drag of up to 9 to 16 pounds force. Next slide, please. When combining both effects, the resultant thrust is then calculated. We estimate that the thrust would have an approximate increase of 94 to 114% to the thrust. In placing the propeller inside the duct, we would essentially be getting the same effect as having two propellers. Ultimately, since this analysis is theoretical, we believe the performance to be closer to the 94% increase in thrust. I'll now pass it over to Marisa.
Hi, I will now introduce the power consumption for the flight team's hardware components. So this table displays the power consumption of the control hardware. So at the moment, we are currently considering a total of 3 inertial measurement units, and the first is the ATIS 16500, which will use 1.98 watts while operating at 3.6 volts. The second option is Kernel 100, which operates at 5 volts using 0.37 watts. And the third option is the AP 10.2, which operates at 27 volts. The power for this unit is to be determined as no current information was listed via the spec sheet. The Ellipse N is an inertial navigation system, which operates at a maximum of 36 volts and uses 0.6 watts of power. The last unit on this list is the FLIR Hadron, which is the camera unit that will help pilot the UAV, which consumes 2.82 watts of power at 5 volts. Next slide, please. This is a weight and cost budget breakdown. So this table displays the weight of each control unit for the flight team along with the cost. And this was helpful in ensuring that the flight team stayed significantly below the total weight budget that was allotted, which was 7.65 pounds. The final weight used from this budget was a total of 6.4 pounds. I also have listed the estimated total cost, which was determined to be $4,998. And it is important to note that throughout the course of this project, a cost budget was never determined. However, we did keep track of the costs that we were making based on the sensor components that we were using. Next slide, please. This is the vision control ground unit that will be used to pilot the UAV. It features toggles to guide the drone to its intended location while displaying a real-time video footage of the UAV surrounding while in the air. Other features accounted for include antennas that allow for the UAV to fly up to ranges of 8 kilometers, and real-time positional measurements, which include altitude and location, as well as the UAV's battery level. This unit also uses Department of Defense grade security, which is compliant with our sponsor, the Aerospace Corporation. I'll now pass it on to Jerry to explain more about the UAV's interface.
Thank you, Marisa. Hi, my name is Jerry. So what I have here is a simple layout of our current flight system. So the left lines represent the power being sourced from our powertrain to our positioning sensors. The red lines represent the sensor feedback and new commands being sent from the handheld controller to our flight controller. The dashed lines represent wireless data being transmitted from our ground station to our telemetry unit and from our handheld controller to our flight controller. So to the left of the telemetry unit, we have our ground station and all the other sensors that are connected to the telemetry unit. To the bottom of our motors, we have our flight controller that consists of a stability positioning controller, and this would be programmed using our control systems team's Simulink models and our sensor architecture. also using the formulas from our aerodynamics. To the top right, 5 boxes, we have the simple layout of our powertrain connected to our motors. Next slide, please. So what we have here, what we originally had for our sensors were 2 separate an IMU and a GPS. So two separate sensors that needed additional controls to compare errors. This would require us to take up additional space and wiring. But with the new AP 10.2 system, this telemetry unit has an integrated IMU, GPS, and altimeter, which allows us to reduce space, allowing us to airstream easier. This system also has 12 RPM sensor inputs, which allows us to connect our motors directly to the telemetry unit to monitor how fast our motors are going. This system also has a pitot tube. This pitot tube uses pressure from flowing wind entering into the pipe to measure pressure, which will then be used to calculate acceleration and velocity. This system also uses a control area network that allows the microcontrollers within the telemetry unit to send data from one another, allowing us to analyze data much quicker. This also has a receiver that allows us to connect to a ground station where we can monitor the current UAV's position. Next slide, please. So what we have for the ground station or a ground monitor is this APX ground monitor. It is an open source system that receives live data from the telemetry unit on the UAV while flying. It uses Google Earth to monitor its current position and future flight paths. On the top left of this image, it shows real-time telemetry data being fed, and we'll be able to monitor this alongside the live camera feed. So the pilot would actually see both this and a live feed, which will allow him to navigate better. This system allows us to actually adjust the flight path. We wouldn't be necessarily using this to control the UAV, but to make minor adjustments. The flight controller itself will be making live changes, but this ground monitor allows us to make adjustments. And since we aren't able to actually fly the UAV itself, this system is able to use a flight simulator to simulate actual flight before the UAV is actually built. And I will now pass it over to Mohammed for control systems.
Hello, my name is Mohammed, and I'll be discussing the methods for modeling and simulating the flight control architecture. The flight control subteam utilized Simulink and MATLAB to create, model, and simulate our control system architecture, as well as analyze the flight performance. And we performed trade studies to determine some of the key components, as well as parameters that needed to be set in order to develop a functioning model for the UAV. And with the knowledge we gained, we implemented it into Simulink, and in this presentation, we will demonstrate our simulations of hover and controlled flight. Next slide, please. In this slide, I'll be talking about the control system variables of the flight control system. Some of these variables and parameters are listed below, such as the applied forces, moments, and inertias, the desired and input, thrust, roll, pitch, yaw, and altitude, the mass of the UAV, the 7 propeller locations, and the optimal pitch angle for forward flight. Next slide, please. And these are some of the measured vehicle variables: the angular rates, the angular accelerations, initial and real-time feedback, velocity and position, and the roll, pitch, and yaw Euler rotation angles. Next slide, please. This slide shows the reference coordinate system that the UAV uses. And it's important to note that -z is denoted as positive z. So forces in the -d direction are driving the body up, and forces in the positive z direction are driving the body downwards. Next slide, please. This is a screenshot of our hover and altitude control Simulink model, which consists of 3 subsystems: the 4-propeller subsystem, the ducted fan yaw subsystem, and the airframe subsystem. And the inputs to these subsystems are the thrust, roll, pitch, yaw, and the gravity. And the 2 subsystems separate the 4 propellers used for maneuvering the UAV, and propellers 1, 4, and the ducted fan, which serve to counteract the induced torque of the ducted fan. The 2 subsystems contain functions to find the respective moments and forces of the UAV using the X, Y, Z coordinates of the propeller locations. And then these forces and moments are added into the airframe, where its outputs are fed back through PID control to allow for controlled hover and altitude. Now Alan will look into these subsystems.
Hello, my name is Alan, and in this subsystem, our thrust, roll, pitch, and yaw commands are turned into forces, which are inputs to MATLAB functions, converting them into moments. The R cross F block you see in the middle are the moments caused by the propeller location about the center of mass, and then you see all the forces and moments are then added together, which are then inserted into the airframe, where its outputs are fed back through the PID controls. Next slide, please. Here we have our airframe block, where the inputs of moments and forces go into, which then computes useful information showing the current and initial states of our UAV. Some important outputs we obtain are the velocity in the inertia axis, position in inertia axis, and Euler rotation angles. The feedback loop of the DCM output, which creates a coordinate transformation from flat Earth to body fixed axis. The DCM output is basically the direction cosine matrix body to wind block, which just converts the angle attack and side slip angles into a 3x3 direction matrix. Next slide, please. In the airframe model were shown in the previous slide, we then put our parameters of our UAV, shown here to the left. We inserted our initial mass of 100 pounds and also our UAV's moment of inertia about the center of mass. The table to the right shows the 7 propeller location within our XYZ coordinate system, which played a critical piece in the design as well. Next slide, please. Here we have our model, our hover control model, where our initial commands for roll, pitch, and yaw are 0 to show how our UAV hovers. Our input for altitude was 20 feet. The scope to the right shows a simulation of how the UAV attains a stabilized hover mode of a Z position of 20 as specified in the input. And then it also shows how it reaches it in a stable and controlled manner due to our PID tuning. Next slide, please. This model right here represents stabilized position control for our UAV, feeding back in our X and Y command inputs into the PID controllers with the angle feed from the airframe to get a usable pitch and roll command output that are then fed back into the stabilized control UAV system, where we establish hover mode. Next slide, please. And then finally, here to the right, we come back to our input command main system, where we inserted our UAV's desired angles of XY axis of 0.77 and 0.7, which will be used during maneuvering or hovering flight stages. The result of our scopes are shown to the left. The top one shows our inertia axis velocities about each axis. We see velocity on the z-axis of about 8 feet per second until it reaches our desired altitude, then it slows down and goes back to 0. We also see a slight velocity on both x and y axes, which were created by their commands. The second graph shown in the middle shows our position, which for the z-axis we see go to our desired altitude of 20 with no overshoot due to tuning. A slight movement in x and y axis is shown as well, which is desired as well. And lastly, in the bottom graph, we have our Euler rotation angles only about the y and x axis, which eventually go to 0, showing stable and controlled movement during flight mode. Now I will pass it on to Janice, who will discuss more about sensor fusion.
Hi, everyone. So I designed a process to avoid any obstacles. So this is my collision avoidance process. It's made up of 3 compartments: the hardware system, which senses, the communication system, which perceives, and the algorithm system that plans. So the algorithm system consists of visual detection, the extended Kalman filter, and path formulation. The hardware system consists of the LiDAR, the IMU AP10.2, processor, and a camera. The sensors are connected to the onboard processor. The UAV operating system runs on the onboard processor. The sensor's data is published as a message by the UAV OS operating system. The CAN bus is utilized to connect the LiDAR to provide a custom LiDAR message via communication protocols. With the obtained messages, it enters the algorithm system. The algorithm can be used to detect unknown obstacles in real time. The data output from the visual detection is fused with the LiDAR data to obtain detailed spatial coordinates of obstacles. The path formulating algorithm then generates a 3D path based on the obtained fused obstacle data. The 3D path is then sent to the pilot's control panel, where they have the ability to set waypoints for the desired path. Now we reach our conclusion. And to summarize, a UAV with 20-inch central propeller with wings with a span of 12-inch and 6 24.5-inch propellers were designed, and an aerodynamic analysis was performed on the wings and central ducted fan using MATLAB. The current control components are the AP10.2 telemetry unit and the FLIR Hadron camera. A simulating control model for the design was created, tested through simulation, which showed stable and controlled hover flight stages. A collision avoidance process was designed to show the process of an obstacle crossing the UAV's intended path. Now I want to thank everyone, especially our sponsor, the Aerospace Corporation, our advisors, and everyone here today with us. Now you can find us here at the expo. Thank you.